Hi everyone, today a video on the amount of substance topic and specifically looking at empirical and molecular formulae. So the empirical formula is the formula that represents the simplest ratio of the atoms of each element present in a compound. So it doesn't have to be the actual number of atoms present, it could be, it doesn't have to be, but it's always the simplest ratio of those atoms. So it's the simplest whole number ratio, it has to be whole numbers, simplest whole number ratio of atoms of each element in a compound. And so to find the empirical formula, we're going to find the mass of each element present in a compound. This is done by experiment, often by something called combustion analysis, essentially seeing how much carbon dioxide, how much water, how much nitrogen dioxide is produced. Now this may be an actual mass in grams, or it might be a percentage. It might say that there is 50% carbon, 25% hydrogen, something like that. The key thing is that if it's a percentage, or even if it's a mass, make sure that it adds up to 100% of what the compound should be. So if you're given percentages, and the percentages don't add up to 100, the remainder will be oxygen. So if it's 50% carbon, 25% hydrogen, obviously it must add up to 100%, and so the other 25% must be oxygen. Likewise, if you're given a mass of a compound, say it's 4 grams, and you're told it's 2 grams of carbon, 1 gram of hydrogen, because it has to add up to 4 grams, the other gram must be oxygen. So once we've found the mass of each element, we're going to work out the number of moles of atoms of each element. So we're going to use our equation that the moles is equal to mass divided by mR, or AR in this case because we're dealing with an element. And then once we've worked out the moles, we're going to convert these number of moles into a whole number ratio. Essentially look at the ratio of those moles, and a really simple way to do it is just to divide each of the mole values by whichever the smallest one is, and this should give you a whole number ratio. So an example to do it. Let's say a question said, find the empirical formula for a compound containing 52.17% carbon and 13.04% hydrogen. Now the first thing, as I said, is to make sure that any percentages add up to 100. Anything missing is oxygen. So if we add up the carbon and the hydrogen, we find it doesn't add up to 100%. So if we do 100 minus the carbon and the hydrogen percentages, we find we have 34.79% left, and that must be oxygen. Now the way that I do these empirical formula questions is to set the thing out as kind of like a table. So first of all, to have the element written at the top, so either carbon, hydrogen or oxygen. Then to put the mass underneath. Now the mass, as I said, could be grams or it could be percentage. If it's given to you as a percentage, you can just directly use the percentage in place of the mass. So pretend that the percentage is in grams essentially. So we have 52.17 for carbon, 13.04 for hydrogen, 34.79 for oxygen. Then, because we have to work out the moles, the thing that I always do underneath is to put the atomic weight of that element. So carbon is 12.0, hydrogen 1.0, oxygen 16.0. Remember that we always put atomic masses to one decimal place. Then we work out the moles by using that the moles is the mass divided by the AR. So the moles of carbon comes out to be 4.348, the moles of hydrogen 13.04, and the moles of oxygen 2.174. Now that isn't a particularly easy ratio to work with, but you can turn it into a very easy ratio, as I said, by dividing by the smallest mole amount. So the smallest number there is 2.174 from the oxygen. So divide every one of those mole values by that. And when you do that, what you find is the ratio here for carbon is 2, hydrogen is 6, and oxygen is 1. And the reason why we do this is because we'll always end up with one of these ratios being equal to 1. So in this case, our ratio is 2 to 6 to 1. So our empirical formula is C2H6O. Now there might be occasionally a time where doing this ratio gives you not whole number values. It will quite often give you a half of a number. So it could be that you have 1 lot of oxygen, 3 lots of hydrogen, and 1.5 lots of carbon, for example. I've just made those numbers up. In that case, if you have something like 1.5, all you simply do is just times the entire ratio by 2. So you then have 2 lots of oxygen, 6 of hydrogen, and 3 of carbon. So anything, because remember it has to be a whole number ratio. It also doesn't matter too much if we have slightly bigger or slightly smaller numbers, so it could be that our ratio of carbon actually comes out to be 2.01, hydrogen comes out to be 5.98. You kind of get the idea. We round to the nearest sort of whole number essentially, as long as it's not too far away. So our whole number, we always want a whole number ratio. Now the molecular formulae, this is the actual number of atoms that exists in the compound of each element in one molecule of the compound. Now it only applies to substances that exist as molecules, hence why it's the molecular formula. But essentially the molecular formula is what you've been writing down whenever you write down the formula of a compound or formula of a molecule. So it's the actual number of atoms of each element in a compound. Now the empirical formula is not always the same as the molecular formula. Remember, the empirical formula is the simplest whole number ratio of atoms of each element. It could be that there are several units of the empirical formula in the molecular formula. And typically the way that we work out a molecular formula is from the empirical formula. So if we're ever asked to work out the molecular formula, the first thing we need to do is work out the empirical formula. And so to find the molecular formula, and to find essentially the number of units of empirical formula that are in it, we divide the relative molecular mass of the compound that we are given by the mass of the empirical formula. So an example to see if this, we've just said that to find our molecular formula, essentially we take our relative molecular mass of the compound, we divide it by the relative molecular mass of the empirical formula. So let's say that we were given in the question, we were said that we've worked out that our empirical formula for this molecule is CH2, and we're told that the MR, we're not told at this point that it's ethene, but the molecular mass of this molecule is 28. So using our formula for the molecular formula, we take our relative molecular mass that we're given, 28.0, divide it by the relative mass of the empirical formula, 14.0, and that tells us that we have 2 units of the empirical formula in the molecular formula. So we have 2 units of CH2, which is the same as C2H4, and that confirms that it's ethene. So a couple of slides ago I said that the way that we work out the mass of how much atom we have of each element in that compound was often done by something called combustion analysis. And so essentially what we have here is we combust our compound fully in oxygen, and we see how much combustion products we get. So how much CO2, how much water, and if there's nitrogen present, how much nitrogen dioxide is present on complete combustion. So let's say we have a question where we have 0.5 grams of a compound Z, and we're told that it contains only carbon, hydrogen and oxygen, and it gave 1.3 grams of carbon dioxide and 0.5 grams of water on complete combustion in oxygen. Now the reason I'm going to go through this is because the way we work this type of empirical formula question out when it's given from combustion data is slightly different. So we're asked what is the empirical formula and what is the molecular formula if the relative molecular mass is 58. So rather than calculating the moles of our carbon and hydrogen straight away, what we're going to do is calculate the moles of the combustion products first instead. So we're going to use the fact that moles is mass over mR to calculate the moles of CO2 being 0.03 and the moles of H2O being also 0.03. Now we're told that it contains carbon. Our combustion products are carbon dioxide and water, so the carbon has only gone into the carbon dioxide. It's the only place it's ended up. And so since each CO2 mole has 1 mole of carbon in it, the sample would have contained 0.03 moles of carbon. All of the carbon has gone into the CO2. It hasn't gone into the water, it's just gone into the CO2. And so because we have 1 mole of carbon, we can therefore use a 1-to-1 ratio, and so we can say that it has 0.03 moles of carbon. Similarly for the water, the hydrogen has only ended up in the water, it hasn't gone into the carbon dioxide. But now you have to be careful because each mole of water, each mole of H2O, contains 2 moles of hydrogen. So the actual moles of hydrogen we had in our original sample is 2 times the 0.03 or 0.06 moles of hydrogen. So now we have the moles of carbon and we have the moles of hydrogen. What we're going to do is just make sure that, because we haven't got the mass of oxygen yet, it's difficult to work out because obviously the oxygen goes into both the carbon dioxide and the water. So we're going to convert our moles of hydrogen and carbon back to masses. We do this by rearranging our equation so that mass is moles times mR. And in doing that, we find that we have 0.06 grams of hydrogen and 0.36 grams of carbon. And like I said in the previous example, that if we have percentages, we have to make sure they add up to 100%. If they don't, whatever's missing is oxygen. The same in this question here, that if this doesn't add up to the 0.58 grams we started with, then whatever is left over must be the oxygen. And so if we do the 0.06 plus the 0.36, and then we take that away from the 0.58, we find that there's 0.16 grams missing from our combustion analysis, and therefore that must be the oxygen. So we can work out the moles of our oxygen, mass over mR, to give us 0.01 moles of oxygen. So essentially we've ended back up at the same place, having worked out the moles of each element. We've just had to go a slightly longer, more convoluted way to find out what the mass of carbon, hydrogen and oxygen was. So now we have this, it's actually a very easy ratio to work with straight away. 0.03 moles of carbon, 0.06 moles of hydrogen and 0.01 moles of oxygen. Hopefully you can see straight away that that just simply turns into a 3 to 6 to 1 ratio. And so the empirical formula is C3H6O. Then to find the molecular formula, remember we're going to take the molecular mass of the compound that we're given, we're going to divide it by the molecular mass of the empirical formula, and that will tell us how many units of our empirical formula are in our molecular formula. So we're told that our relative molecular mass of this compound Z is 58.0. Our MR of our empirical formula, remember to work out MR, we just add together all of our atomic masses. So we have 3 carbons, so 3 times 12. Remember that atomic masses are given to 1 decimal place, like molecular masses are, so 12.0 times 3, plus the 6 hydrogens, and then plus the oxygen, which is 16, gives us 58.0. And so 58.0 divided by 58.0 is 1. So that tells us there is 1 unit of our empirical formula in our molecular formula, i.e. they are the same formula. So the molecular formula is also C3H6O. So time to have a go at some questions. So we have to calculate the empirical formula and then find the molecular formula. So have a go, pause the video, and the answers will be on the next slide. So the first question was to find the empirical formula, and we were told there is 66.7% carbon and 11.1% hydrogen. So the first thing to do is check it adds to 100%. No, it doesn't. And the remainder to make it up to 100% is 22.2%. So that must be oxygen. So I'm going to set it out like a table again. So I have our elements along the top, carbon, hydrogen and oxygen. Then our masses underneath, which again, remember you could just use the percentages directly as the mass in this case. So 66.7, 11.1 and 22.2 respectively. I then put the atomic weights underneath, so 12.0 for carbon, 1.0 for hydrogen, 16.0 for oxygen. We then work out the moles, remembering that moles is the mass divided by the AR in this case. That's why I would write the mass and then the AR underneath it to kind of almost visually work out the moles. So the moles of carbon, 66.7 divided by 12.0 is 5.56. Same thing for the hydrogen, gives 11.1 moles, and for oxygen, 1.38 moles. We then need to find our relative ratio. Remember to do this, we're going to divide all the mole values by whatever the smallest one is. The smallest one here is the oxygen, 1.38 moles. And so dividing each of these mole values by 1.38 gives us 4.04, 8.07 and 1 for carbon, hydrogen and oxygen respectively. Now, as I said in the video, it might not be a precisely whole number ratio, but we can just round down and say, well, 4.04 is 4, 8.07 is 8, and the 1 is a whole number already. So we have a ratio of 4 to 8 to 1, and so the empirical formula is C4H8O. Then question 2 was to calculate the the molecular formula. So we need to know the MR of our empirical formula. So this is 4 times 12 for the carbons, 8 times 1 for the hydrogens, and just 16.0 for the oxygens to give 72.0. Remember, always give MR values and AR values to 1 decimal place. And then we were told that the molecular formula, the MR of the compound was 72. So we do 72 divided by 72 is 1. So we have 1 unit of our empirical formula in our molecular formula, and so the molecular formula is exactly the same. It's C4H8O. So thank you for watching this video. You can find many more like this on my YouTube channel. If you found this video helpful, please consider leaving a review on a tuition website. I offer tuition online for chemistry, so please check my tuition pages if you're interested in that. And if you need any more help with your chemistry, feel free to drop me an email. I'll be happy to help.